Okay, so for number two, the first part here, part A, I don't have all of the exact values here that we were using from the original code, so I'm just going to kind of talk generally about what this is looking for. So we're saying the Kyle board is broken and we can only use a DAC count val of 250. What are the two things we could change to modify the code given in the GPDMA notes to generate a sinusoid with frequency 781 hertz? So here it's sort of important to remember that what we're basically doing here is we're setting up a sinusoid wave in an array, but essentially we're just sampling points between 0 and 2 pi. So we're putting a single wave of that sinusoid, and then we are generating it or putting it into the DAC at a faster or slower speed in order to make it go through that sinusoid quicker or slower, and that's essentially what makes us be able to play a different tone, is by running through that wave quicker or slower. That changes the frequency. So from the lab we did, there's an equation that the period is equal to 1 over the p clock times DAC count val, which is how fast we're putting a single sample into the DAC, times the number of samples. So DAC count val times the number of samples is sort of the full wave, and then we're dividing that by how fast the clock is running, since these are basically cycles. So this is a number of cycles that we're going to take to do each sample. We divide that by how long each cycle takes on this processor, and that gives us the time, the period. So obviously from this equation, if we can't change this middle value, there are two other things we can change, which are the p clock and the sample numbers. So we can have either less samples, which gives us less resolution, so less points on that single sine wave, but it would make them go faster because we're basically only putting some samples into that DAC, and we're putting them in at a fixed rate. DAC count val is not changing, so we're putting less cycles. We're taking the same number of cycles, but we're putting less samples in, so that's going to be less total cycles and be a higher pitch note. Or if we have more samples, that's going to generate a longer period and therefore a lower pitched note. The other thing we can change is the p clock, so that's how fast the processor or the peripheral clock is running for this particular device. So we can either divide that further or multiply it or make it faster. So if we look at the notes here, we'll see that right here, the p clock select for the DAC is being set to 0, 0, which is equivalent to 100 over 4 megahertz or 25 megahertz. So we could make this wave a little bit slower, a longer period by further dividing the p clock, so making it 100 over 8, for example. Or we could make this wave faster by making the p clock 100 over 2 or 100, just 100 megahertz. So those are the two ways that we can sort of adjust the frequency of the wave being played over the speaker. So moving on to the next one here, it asks us to write an assembly loop that copies 1024 bytes of memory from address 0x100000 to 10004000. So I'm going to write some assembly code. The first thing I'm going to do is just put those values in the register. I'm using the sudo instruction LDR to take this address and put it into R0, and then take that address and put it into R1. Then I'm going to basically figure out what the end address is. So I want to copy 1024 bytes, which means I want to move from this address up by 1024. That's going to be my sort of exit condition. So that's when I'm going to stop copying memory. So I'm going to put R2 to be R0 plus 1024. So R2 is going to be the register that I'm going to check to see did I get to that point. So here I'm making a loop, which is just a label and then some instructions. So I have a loop label and I have an end label. And I'm going to do a comparison of R2 and R0. So I just said that R2 is going to be sort of my counter for the end of, or like my marker for the end of the 1024 byte region that I want to copy. So I'm going to compare these two, and I'm going to check to see if they're equal with the BEQ. If they're equal, that means I've reached the end of the region that I wanted to copy, so I'm going to jump to end. If they're not equal, then I'm going to fall through to the next instruction. I'm going to load from the address R0 into R3, and then I'm going to store the thing that I just loaded from R0's address into R3, I'm going to store that value from R3 into R1. So this is essentially just loading something from memory into R3, storing it right back into the address at R1. I'm then going to increment both of these by 4 here. And the reason I'm going to do that is because I want to copy all 1024 bytes, but a loader and a store, a load and a store are actually doing 4 bytes at a time. And so that means I can increment by 4 here. I'm actually kind of batch processing this instead of doing a single byte at a time. So I could also do a load B and then a store B here. And I could do add 1 to each of these, but that would take me more cycles. So this is actually saving us a little bit of time because I'll only have to do this 1024 divided by 4 times instead. And then I'm going to jump back to the top of the loop. And the top of the loop, I'm going to compare again. So once I do get to 1024, I'm just going to BEQ to the end. I'm going to jump out of this loop. And that's all I have to do to copy that memory. So this is kind of showing like without DMA, this is what I would have to do, right? I have to load from some memory address into a register, and then I have to store that from that register into some other memory address. And DMA kind of cuts that out, cuts out the middleman here. And just takes things from one address and puts them in another address without having to have the CPU loaded into a register and take up register space. And of course processing time. So the next part here, part C, is how many cycles would the code from part B take to execute? Assume that the taken branches cost 3 cycles, loads and stores cost 2 cycles, and all other instructions cost 1 cycle. So we could look this up in the Cortex manual. So this is reference D on the course website here, in case we ask you something about the runtime of a piece of code that we don't give you everything for. So we could look these up and see that an add is 1 cycle, etc. But here we're just basically given everything we need to know. So each load is going to take 2 cycles. So this is 2 plus 1 for the add. So that's 5 cycles before my loop. So that's what I'm going to calculate here. That's sort of, beginning, that prelude to the loop is going to be 5 cycles. And then I'm going to calculate how long this loop is going to take to execute. So we can see that each time, I'm doing this for 1024 bytes. That's what I've sort of, set my end condition at. And I'm adding 4 each time. So let's see what 1024 divided by 4 is. Okay, so 256. So my loop is going to execute 256 times. We should sort of be familiar with the fact that when a loop executes, it's going to do the same thing until the last iteration, and that's when it's going to sort of break out of the loop, right? So it's going to execute 255 times, where it's going to loop back to the top, loop back to the top, loop back to the top, and then the very last time it's just going to do this comparison, and then it's going to jump out of the loop using the BEQ. So that's what we're calculating here. Is there are going to be 255 iterations of 1 plus not taken, so 1, plus 2 plus 2 plus 1 plus 1, plus a taken branch, which is going to be 3. So that's the first sort of clause here, which is 255 iterations of 1 plus 1 because it's not taken, plus 2 plus 2 plus 1 plus 1 plus 3 because it is taken. So taken means we do go to the label, like we actually change the position in the code and go there. If we just fall through, it only costs 1 cycle. And then my last iteration, so when I exit the loop, I'm going to do the comparison for 1 cycle, and then I'm going to do the BEQ, which is going to be taken. I'm going to take that to the end label, so that's going to cost 3 cycles. And if we add that all up, it gets us to 2814. Okay. So part D then, what is another disadvantage of running the code in part B instead of using DMA? So the idea here is that if I used DMA, it would cost about 256 cycles because I'm only really doing this copy from memory, and DMA is only going to cost about 1 cycle. So I'm saving roughly 2,500 cycles here, maybe a little more, 2,600, in order to do this with DMA as compared to doing it in the CPU. Because DMA doesn't have to do all this extra stuff like comparing and BQing, adding. It's just kind of doing that in the hardware, and so it's specialized, and that makes it a lot faster. So that's the one advantage, which is that it's taking a bunch of time in addition to what it could be taking. So what is the other disadvantage? Which is that it doesn't occupy this occupies the CPU's time and DMA does not. So DMA is sort of in the background that allows us to have a main loop that we can do animation or something else with our code rather than doing all this copying of memory. So the CPU can do something else at the same time.